Hello. We're going to work on a fourth compiler, environment, possibly operating system. I'll explain it more as the stream goes on, as I get into it. I've not done a programming stream in a few months now. I want to start doing them more. Believe me, I do. But it's been a minute, so this is kind of a test stream. I have to kind of find my feet in here again. We're going to get started. I was working a little bit already. And over the past couple of days I've been working on this. It's actually, the basis of it is porting a previous fourth that I started. That one was based on Jones fourth. So I copied and pasted a lot of my old code. That one's for 8086. I want this one to be for 386, so I'm adapting that. So right now the situation we're in is trying to get the fourth dictionary full of the words that we need for the compiler. I might go more into what fourth is and how it works a little bit later. I don't want to start there though. I kind of want to get warmed up on some coding. So right now I'm creating a string type. In my previous code, I just had the string as a sequence of bytes and kept the length of it in a register. That's how Jones fourth does it, and I was pretty much copying that one-to-one. Now I want a string structure where the length is always at the beginning of the string. So I've created that, started using that in parts of the code. We're going to create a copy function because I want to make a copy of a string here. So we got string ASM. That'll be the file with the string routines in it, and assembly. This is all 386 assembly, by the way. And I'm playing the input to be the DS ESI register. Will have a pointer to the source. EDI will have a pointer to the destination memory to make the copy. And I can more or less copy and paste this, I believe. This is our structure definition. So it's called S8N for signed 8 counted string. And the first byte is the length of the string. Everything else is the data. So it's a variable length structure. So we can use these as offsets. So we're going to use a repeat, move SB instruction, and I'm pretty sure that CX needs to have the number of bytes. Copy. Yeah, it looks like CX. I'm not very good at x86 assembly language. But you get good through practice. So ESI points to source. It means ESI points to the length right now. Now we want that to be in CX, but it's actually a byte. So we need to 0 extend. Then we increment CSI, point to the data instead. Data, part of the string. Doorbell. I'll be back. Okay, I'm back. Where were we? Okay, maybe we won't increment ESI there, because I actually want to copy over the length byte as well. So then we would add 1. Add 1 CX. And repeat. And that kind of looks all right. We'll find out. Let's try it. So we replace all this. The operation here is to make a copy of the string on the stack. So if we're going to do that, we need a length routine also. And that can even be a macro, I think. It might be better suited to be a macro, but we'll start out with a subroutine. That may work. So at this point, EDI register points to our string. Let's move it over to ESI. Now we find out how long it is. Now the CX register is a length. Now we make room on the stack for it. We're getting the length of the string. We really need the length of the structure for the copy. I may want some sort of size macro for the structure. I'm not sure what to do there, but for now, increment CX. So we got the size of the structure instead of the string. Make room on the stack for it. Make the copy. Now EDI points to a string, which is what this next routine expects. However, it expects it to be in the registers, not in the structure definition that we made, so we fix that next. So let's test this. I'll set a breakpoint here. And I'll set a breakpoint here right after we do it. And we can try it and see what happens. Here we're at first breakpoint. So I made these GDB functions in Python. These GDB functions print the value of the string, our structure definition of the string. GDB doesn't know about it, doesn't know what all this stuff is. So I wrote Python module to interpret it, print it for us, and that should make it convenient. forgot to do this. Gotta move the stack pointer. Doesn't matter, we just need to see if this thing works the way that we want. So now we're at the mixed breakpoint here. This stack pointer should point to a copy of the string, and it doesn't, so what's our problem? Oh, this is going to expect EDI to point to the memory to write to. So EDI needs to have the stack pointer's contents. Okay, that looks right. So you got the one string of length 1, and then the colon is the character. I'm not sure why ESA gets this value though. Let's step through and just take a look at what we did. Oh, because we pop it. Okay. Okay, so we're ready to work on this now. So this is find word in the dictionary. Currently it expects the EDI register to point to where the string starts in memory. We wanted to point to the counted string data structure instead. So before, then after, address of SADN string. So we're pointing to our data structure here. All this stuff has to change. All these routines that evaluate strings have to change. Convert string to uppercase. Okay, let's see where in the code we use this string uppercase routine. Almost nowhere. Just that one call. So we're actually going to change this. We're going to call it SN8 upper, or S8N upper, for that consistency. Okay, so this routine converts a string to uppercase. So now we won't send CX in. We won't worry about what CX is. We're going to look at the data structure. Because again, the first byte of the data structure is now the length. So we have to get the value of the length of the string into the CX register here in this routine. Like so. We're going to increment EDI for this operation because we're going to loop over it. So let's push it before we're going to begin, pop it before we leave. So as not to destroy the value. Increment it, so now it's pointing to the front of the string. Actually, I suppose we don't have to do this push and pop of the EDI because we're not actually changing EDI here. We're using the Lotus B instruction, which operates on ESI. So we can move EDI into ESI, increment ESI. That's already pushed and popped. So now the rest of this routine mostly stays the same, I believe. We're uppercasing the entire string here. If we're outside the boundaries of letters, then we do nothing for the character. Otherwise, we subtract x20 from the character's value, and that'll uppercase it. We need ESI here, since we're converting our 16-bit code to 32-bit. And I think that works. We'll test it on something later. I kind of want unit tests for this stuff. I did not find any x86 assembly language unit testing libraries. So maybe we'll write one or start on something like that in a little bit. I would like to have some tests. But let's call this good for now. We'll find out what's wrong later. Now at this point we can test this find function. See if this routine actually finds the words in the fourth dictionary that we're looking for it to. So we're going to break at this function 341. When we break, it's going to print the value of the current dictionary word that we're iterating over, because find iterates over the dictionary words. I suppose actually we'll break a check word here, because this is where the loop starts. So that's line 345. Let's see how it goes. Okay, we're pointed to a word here for EBX, which is what we want. EDI should be also pointing to a word, or a string. And that's not right, so we've got a bug somewhere. Let's go back. $248. Okay, I don't see our string in memory here, so let me revisit all this. In fact, let's step through. we take a closer look. So what's in the ESI register, because that's what's going to get copied. That is our string. Make room on the stack for it. That's 2 bytes on the stack. Stack point is a destination. Oh, a problem, or at least one problem, is it's incrementing the EDI register, and we don't want it to do that. The MoveSP instruction increments the source and destination registers. But we need destination registers to stay where it is. Actually, no, it doesn't matter because we do want that anyway, but just don't think it matters in this case because over here we move stack pointer into EDI. What's stack pointer? Yeah, it's pointing in the right place. Whoops. Yeah, it's pointing to the copied string. Oh, but stack pointer changes when we pop there. Yeah, so I need to move this pop for the ESI register here, I think. So we don't mess up the stack. So we push, reduce the stack pointer for the copied string, add it, then pop. I believe that's correct. I'm not sure we really need to make us copy the string on the stack anyway, but that's a different matter. All right. Now we're in a find routine. And this is the string to find. This is the dictionary entry we're currently looking at. So that is how I expect right now. Now let's step through. So these dictionary words are this kind of linked list, each one pointing back. We started the latest one, and it points back to the one before. The link field here in the data structure points to this address, 2010FO. Then in the next iteration, if we don't find the word, we're now examining that address. That's the beginning of the structure that is for a different word, points back to the previous word, the word before it, on and on and on until we're out of words. So the word that we're trying to find is just the colon. Okay, so iteration is working. So instead of single stepping, I'm just going to hit that breakpoint. So we are at the colon here, so in this routine find is intended to find that word and return with its address in EAX. So let's see if that happens. Nope, and it doesn't because CX register's value is incorrect. So we need 2. We need to look at the data structure for the length. The current code relies on it coming in the CX register, and that's what we haven't changed yet. So I believe this will be the right place to do it. No, before. And we'll do it right here. We already have a length. A length routine. I believe that should do it. Need to move the location of that breakpoint, but actually, instead of doing this by number, I wonder, maybe I should be able to do this. Find.checkWord. Might be able to tell GDB to stop there. break at find.check word. Yeah, that appears to work. There's a breakpoint in the right place. Okay. Here's the colon, so this is the condition where the word should be found. So what this code does is see if the word's length that we're looking for matches the word in the dictionary that we're iterating over. And if it doesn't, we quickly know that we go to the next word instead of comparing character by character. If the lengths do match, then we go ahead and compare character by character. So we're now on that character comparison. So we have this character by character comparison here. I want to do this in a routine for the string. So it's reusable. So we're going to make a s8n comparison subroutine. And then let's compare character by character. So push the registers at the beginning of the subroutine and then pop them at the end, because we're going to modify them. Increment both by 1. Actually, no. We won't increment them. Well, we need to get the Regan's repeat move instruction, so CX needs to hold the number of bytes we're going to compare. I said repeat move, I meant repeat compare. So to do that, we're going to call that s8n length. Now CX has a number of bytes to compare. I said it wrong and then typed it wrong. We use a rep E there. The difference again? Repeat until CX is not 0. By non-matching, right. So the 0 flag will be set if there are any non-matching bytes in the range that we're asking it to compare. Now the problem here is the dictionary entry is actually not this data structure. It almost is. but it's not quite, so I guess we do have to do, we can't make this a subroutine at this point. So what we'll do instead is leave it CX at this point. Hold the length of the word we're looking for. We're loading the name of the dictionary entry into ESI. EDI points to the start of the string data structure, which points to the length byte. We need it to point to the data instead. Do a comparison. Restore registers that we want to preserve and go to check the next word if there's not a match. So let's try this out. I made that label compare full. So we can set a breakpoint there. So let's try it. Okay, we're at compare full. We've got our source word and our dictionary word. They should compare correctly. Zero flag set. Now we found the word. So for this case, that's working. We're finding the colon word, which is what we need to proceed here with the compiler. So we use the ESI register to make that copy of the word for the find routine. We're done with it now. So we can restore the stack. Now what's all this code doing? Okay, so at this point we are testing to see if we've got a literal. And that's if the word's not found. So we don't care about that right now. This is if the word is found. I should rename this label. I may come back to that. Or actually, let's do that. Set another breakpoint. Okay, we do end up there. So I got to refamiliarize myself with what all this code does. Code field address, I believe is what CFA means. Code word address. This is probably going to be wrong. These are probably sizes for 16-bit 8086, so we'll probably have to change them. So our input D is the DI, is the address of the dictionary entry. And we're gonna have to change that to EDI for sure. Since we have 32-bit addresses now, we'll go ahead and do that. Here too. This is all related code. Okay, so we do some stack tricks here. What we're doing here is moving the flags byte into the AL register. We need to change this because that will now be wrong for our data size. We do have a structure for dictionary entry now, so it's going to be flags length. That's the structure member we want. So we're going to change it to something, change that +2 to something like this. And there it corrects that part of things, I believe. So now in code field address, EDI points to the address of the dictionary entry. And we're doing some funny bit tricks. Address of the code words. I believe what we're doing here is skipping past the name, which is a variable length. And finding the code word field. Let's take a look at John's Fourth and make sure. Yeah. So this is kind of this is the illustration of the data structure. So if we make this larger, you can see it. Link pointer, that's the address that points to the previous word in the dictionary. This is the code word, so the length of the word and then the actual name of it, the string. Padding is padded to, what's it padded to? Padded to 4 byte boundary. And then this is the code field address. So this is what we're trying to find here. Okay, so we're adding 2. This is just copied from Jonesforth. Adding 2 because we know that's a size. We can take advantage of our structure definition. What's it called? Excellent, I believe. Yep. So now magic number 2 goes away, and it doesn't matter how big. Doesn't matter how big the size of the link pointer is that we're skipping over. This becomes more portable. The assembler's complaining about different sizes. That may do it. Let's see. There's the name. This is our padding, I suppose. These 2 bytes gets us to the next 4 byte boundary. I think that's right. And here, okay, so colon. So if we just look at our symbol table, we can know what's going on here. Two 21070. Okay, yeah, so colon. Here's where the dictionary entry starts, and then this is the code word address, which is what we're looking for in this routine. So 21078x. 21078. Okay, so out of this CFA routine, that's what we expect. Yeah, EDI does not look right there. Oh. Programming error. Is that right? I'll be good at assembly one of these days. Doesn't look like we rebuilt properly. Nope, that code is wrong. Okay, better now. Oh, no, it's still wrong. No, I'm changing the wrong code. Okay, helps to change the right code. Two 21076, and I think that's not quite right. 21078. And that's because I converted this for 16-bit. That's right. EDI has what we want in it. 201078. Okay, so we have the address of the code word. Now we're back here, and if it's an immediate word, we execute it immediately. And the words are marked whether they're immediate or not. Colon's not, so we shouldn't run that code. Okay, so we don't execute it immediately, we go to state check. And this code is checking the current compiler state. If we're not in compiling mode, we execute the word immediately. If we are in compiling mode, we do this other stuff instead. I think right now we're not going to be. Yeah, so we got to execute immediately. I guess we can actually look at the source code here instead of jumping back and forth from the editor. So we're not in compiling mode, so we here let's look and see if our byte's literal. I'm going to turn this disassembly off. So let's do this here. Let's not show the disassembly by default. Let's give ourselves more source code. There we go. So we're not compiling right now. It's not a literal, so we don't execute it. BX should contain the address of the word. And that doesn't look right, so let's see where BX is set. Move AX, BX. Okay, that may be because... Yep, we moved AX instead of EAX. So we need to be working with EAX and EBX. I guess we're not worried about preserving registers anywhere here, so we can probably just change this. Whoops. Skip past what I wanted to investigate in there. Okay, and that's what we want. We wanted to jump from interpret to do call. Now let's take a look at what do col is supposed to do. Do colon. We push ESI on the return stack pointer. Return stack forth has two stacks, a data stack and a function call stack called the return stack. So at this point, I believe what we're doing is so we're pushing ESI, which points to the currently being executed word, I believe. I don't think ESI is right, so let's take a look at that. Let a breakpoint at the beginning of interpret, or we're gonna just take a look first. We push and pop it, so I think we should be okay there. But let's just see what happens. So ESI is 20105C, and that should not change from beginning to end of the routine. At least I don't think it should. Okay, so we pop it and it becomes 20105C3A. I think at some point we mess up the stack here. Oh, we probably mess up ECX. Find. And we overwrite ECX and copy, which I didn't intend. It's overwritten by the length subroutine. And here and find. So we'll save it and restore it in both those teens. This is trickier because we have multiple return points. But not too hairy. So push EVX, ECX, ESI. Okay, so let's try that again. And 20105C. It's going to change. But it gets restored. That's what we want. Now we're at do call and it looks right. Okay. So back to do call. Let's look at Jonesforth because I'm fuzzy on these details of how the fourth compiler is working. Haven't really looked at this stuff in months. Do call is an important word, so there's a lot to say about it, I guess. It's the main interpreter function. So we're pushing ESI on the return stack. Make ESI point to the first data word, so pass the code word. Makes sense. The code word is, I believe, 4 bytes long. Yeah, that's a code word, double. So yeah, 4 bytes. I don't want to have to type 4 here. I want macros or constants that describe this stuff. So let's go ahead and do that. Actually, we'll define code word size to be 4. But the code looks correct, assuming push RSP is written correctly, I believe. So it should skip to the next word, whatever that is. Okay, here's where we are right now. We're processing colon. So that do call should start pointing us to word, which should get the name of the new word that we are compiling. This is the fourth code that we're trying to compile. Test 1. Just to show, we'll take a working fourth system, I think. G4th. There's nothing on the stack. Type test. Whoops. So, clear that. Try it again without mistakes, hopefully. There's nothing in the stack. We compile this word called test. Colon starts compilation, then the next word after colon is the name of the word that we're compiling. Then we've got the definition. I've just got a 1 there, which means that we're going to put a literal 1 number on the stack. Then semicolon ends the definition of the new word. So then we investigate the stack again. Again, there's nothing on it. I forgot to do this. Type test. This is okay. Investigate the stack again. Now we've got the 1 on the stack. So the typing test puts the number 1 on the stack. A very basic case. So we want our fourth to do that also. Okay, so these are all the things that colon needs to do. So we need to get the name of the new word, create the dictionary entry for it, and then put all the things we need to put in there to actually make the whole thing happen. So we've got the std word. Then we've got a definition for word, which does all this stuff. So once do call's done, because next macro, we should end up in this code. Word is. So let's follow through our decolon subroutine and see where we end up. If we look at our symbol list here, this whole business word, I believe this is where we want to go. So yeah, we're in the right place. Good old 200209. Okay, so if that subroutine call works correctly, we should get the string text or test. Next word after the colon, and that did work. This is wrong though because we moved to the string data structure. What I believe this word is supposed to do is push the string onto the stack in some way. I'm looking at the ands forth specification. Yeah, looks like it. Push the length and its address. So if we take a look at the stack here, yeah, the length is 4, the address, I'm trusting that's the address. Oh, but it's not the string data structure, it's just a regular string. Yep. Okay, so once we're done in Word, we need to do create, and I don't think we've copied over create yet. Nope. So let's start to work on that. And again, copying and pasting most of this over and adjusting it as I do it from the other fourth that I worked on. This is our create subroutine. Okay, so same business here. We're gonna have to convert all this stuff over. This is error handling. That makes sure we don't go outside of the space that we reserve for the dictionary. I want to do that in a different way, so commenting it out. Okay, so the word pushed the address of the data of the string and its length onto the stack. Now the create word needs to use that information. I kind of want to create a structure for the fourth counted strings. They're represented a little bit differently in memory than ours. The one that we're using in assembly here. We're going to come back to that though, because I'm going to think about it. I may just change our string structure. So for now, let's work on this a bit. I don't know that we'll add all these words. We have to do all this to get a word compiling correctly. I'm not sure we'll do all that right now, but let's at least look into this a bit. CX needs to change to ECX all throughout this routine. EX also needs to change to EBX. I've nervous I did that too many times. Let's see. So ECX, that looks right. BX, we're still in the right place. Okay, EBX. Same for DI. That needs to change to EDI. We're in 32-bit land. AX will become EAX. DX will become EDX. Let's look at where else we're using DX right now. I want to make sure we're not invalidating any assumptions around what the value of dx is. No, doesn't look like it, so we'll just change. We use it very sparingly here, I guess just temporarily. SI becomes ESI. And I believe we are sized properly. So let's walk through this routine so I can remember how this works and what it does. This whole routine creates a new dictionary entry for the word that we're defining. First of all, we see if the word's already in the dictionary. If it is, we redefine it. We print a warning message somewhere when we do that. That appears to be all this code does, and we'll rework all this. I want to comment this out, but I don't want to forget about it. I'm going to add a to-do routine to just halt when we hit some code that needs to be implemented. That should do that. So let's test that out. So here's the code I'm going to comment out. And we'll replace it with that to-do subroutine. So now we should hit that. Oh. Got to take care of the error messages. Okay, so I made that lowercase. Do we hit our to-do? Doesn't look like it. let's set a breakpoint at create and make sure we're getting into create. Oh, we need the def code macro for this since it's only assembly. Almost got there, but it looks like we reset with a triple fault, which means probably messed the stack up somewhere. I want to set a breakpoint at colon. Okay, I need to tell the assembler that these code labels are global. Or maybe that wasn't the problem. Should be code underscore colon, actually. Oh, there's no code for it. It's a fourth word, not an assembly word. Okay. Okay, so we can't do that, but we can set a breakpoint at create. Okay, so if we call to do, we actually halt with the to do on the display here, which is what I want for now. So we're not hitting that code because it's in a condition of if we're redefining the word. I'd forgotten that. So here's where we're creating our dictionary data structure. This variable, var here, it's an assembly language variable that we create with the some of the fourth macros we have. So it holds the address of the next available place in the dictionary. So the byte after the end of the last dictionary word, I believe. And then latest points to the latest entry in the dictionary. So free space, entry. So we're building the dictionary entry, and I want to use our data structure. Here's our structure definition. So we get a length field, flags field, name. Name's variable length, so we can't do the other stuff. We can't put code word in this structure because it's variable length. Okay, now when we come in here, what does ESI point to? ESI 201088. Points to the current word. The word we're in, which is create. This would store the address of the current word into the link pointer, which I don't think we want. We want it to point to the latest word. Let's look at Jonesforth. Did I make a change, or did Jonesforth have this? Oh, that's correct. Yeah, we're not storing ESO, we're storing AEX. It's not a move instruction, it's a store instruction. It uses the accumulator. Okay, so EDI is where we're storing it, destination. That's our empty space, that's right. Latest is our link pointer value. We're storing a double word. since we're in 32-bit land now. Okay, so we expect CL to store the length of the word that we're adding to the dictionary, and that looks correct. It should be length and flags though, is that right? Yeah, it is right. We're only storing the length right now, so I guess we come back and add the flags to it later. EBX is the name. So we're copying the name into the new dictionary entry. This needs to change to 3 because we're in 32-bit land. And when we're done, we update latest to point to the new value, which is where here the empty value was pointing. And then make the next empty value point to after our new entry. So let's take a look at that. It's not found in the dictionary. So here is 207108. If we look at our list of symbols, our dictionary stuff should be in there. Two 7108. That's the top of the return stack, is that right? That doesn't seem right, so let's look at how we define here. Yeah, that's wrong. Here needs to be initialized to after our last word, so where the link pointer ends up, or after that, when we initialize all the built-in words in the assembly code. So let's figure out how Jonesford does it. Actually, let's look at my previous implementation. Oh, that is right, actually. The built-in words are not in the BSS section allocation for dictionary. They're in read-only data. So thinking about it more, that is correct. It's in a latest EAX 201114. And that looks right. That's the last word. So that's the correct value for the length pointer. So looking at EDI, there's nothing in there. We're going to store a structure there. This is wrong, of course. Whoops, where am I? We need to rebuild. .201, 114. Yeah, that's latest, right? We got bytes in there, so if we print it as characters, yep, 4 bytes for the link pointer, 1 byte for the length and flags, and then 4 bytes for the name of the word. So I think we're looking good there for creating the dictionary entry. At this point, we'd move on to the next word. So that's lit, do call, comma. So this is the rest of the compilation process, all the words that we have to implement to get a word compiled. I'm going to end stream pretty soon. This is meant, again, to be kind of a test stream. Warming up for getting back into the routine a little bit. I want to look briefly into making some kind of a approximation of the unit test library. And then we can test strings, functions, and stuff like that. I think over in my other code repo for the operating system that I made some assertion macros for assembly language. So we can take a look at those. Search for assert. Looks like we have a few things. Assert memory. So that compares memory areas. This one may look at register contents, so let's take a look at that file. Insert. Where's it defined? There we go. Got to search for INC extension files also. So this macro is meant to compare register values, I believe. So what we want is a set of macros, I think, that approximates a unit testing framework, something like check for the C language. So let's look at the basic use case a little bit. If we want to find out if the string routines are working, for example, length, copy. Let's hack something in here. Let's create a test string ASM file. Let's get this in our build system definition. And then back in our fourth file in the startup, after we get done with the setup, actually before that, let's see, as soon as we start, call test string. Right now we should just get a to-do message once we run this. Nope, what happened? Oh. Now we don't have to include anything. We have to say extern to do. Okay. So what I want to do here is let's test some stream functions if we can. So we'll set up our sections. Call our dev string macro, and we'll just call this, I don't know, my test. And we should be able to print it. Gotta include our macro definition for strings. Okay, so we print it, that works. So what I want here is an automated test. And we could write functions to do this. But I think we would want macros. But let's just riff on it with functions for a second. So if we were to create a private function, test length. After that call, the CX register should have the length of the string in it. So we print a message, pass or fail. If we're not the right length, we print fail. If we are the right length, we print fast. Test passed. So I want to set up a series of tests like this for different modules, video and string and stuff like that. I don't want all this code every time. So I want the test to be something like this, like replace all this stuff with something like that. And that's what I'm looking for. I don't know what we can achieve with NASM's macro system. I've got the examples, so I have some idea of what we can achieve. I wrote all this a long time ago. Let's try something. So let's create a test.inc.include. So I set up this macro. This macro takes a few arguments. The first is the size of the comparison. The next two are well, let me take a look before I start talking about it. Okay, size of comparison, argument 1, condition, equals, not equals, etc. And then argument 2. Which, I don't know, this may be good enough. Let's try it. So here's our okay. Here's our failed. We kind of want fail first because we still want the registers available here with our argument values so we can print them. I think this inverts the condition. Let me take a look at the NASM manual around the macros. Yeah, inverse. So we want it like this. So if we match the condition that we're asserting for, then we just jump to exit. If we don't, then we fall into fail here, and then we do stuff. So back in our test. So I think that's close to what we want for an assertion. Let's kind of give this a shot. Assert word. So CX, E for equals, and 7. So let's see if we can force it to fail and run. Not taking 4 parameters, okay? Wants 5 parameters. Oh, because I think we called it through another macro. Yeah, we got line and stuff like that. Line information, which I remember that not working. But let's see. Let's take a look. Expression syntax error. Maybe it doesn't know what byte is. Yep. Okay, that works. Now let's make it pass again. So we got the most fundamental of unit test cases working. Now, of course, this is just the most basic case. We need to be able to run several tests in a row, report on when things fail and stuff. So I'll think about it. It would be nice to have, if we're going to have a lot of assembly language supporting the 4th. We'll need one written in 4th also. So I think that'll do it for this stream. Thank you, anybody that came in and viewed, enjoyed. I will be back in the next few days.